We're going to finish up Chapter 5 today, starting with time plots. So time plots are only a small part of statistics, but they are useful when we're interested in looking at how data behave over time. So, for example, still using the average wind speed, we can see the average wind speed for each day over the course of a year. This allows us to see how the data progress as the year moves on. So we can see that at the beginning of the year here, the data are fairly spread out and we have quite a few windier days. As the year progresses, as we get about halfway through, the data become more consistent and it's less windy. And then finally, as the year comes to an end, the data become more spread out again, and again we get windier, and we can see that we even have an outlier up here around 9. Again, overall, the time plots are just showing how the data progress over time. Moving on to re-expressing data. We're going to talk more about re-expressing data in Unit 2, but for now it's important to know that there are times when it is important to re-express data. Those situations are when we have extremely skewed data, as we do in this situation. So here we're dealing with the annual compensation of CEOs, and we have a very large range, and it is extremely skewed to the right with an excess number of outliers. When this is the case, it's hard to define an actual center or spread that is useful to us, so we try and re-express it to make the data more symmetric so that it's easier to identify a center and have a more manageable spread. So again, when the data are skewed, it can be hard to summarize them simply with just a center and spread. It's also hard to decide whether most extreme values are outliers or just part of the stretched out tail. So one way to make a skewed distribution more symmetric is to re-express or transform the data by applying a simple function. So here we applied the function of a logarithm. So we took the log of all of the annual compensations. Another way to apply a transformation is to take the square root, or to square the data, or to take the reciprocal, or something along those lines. Again, we'll talk more about this in Unit 2. But here, by taking the log of the annual compensation, we made the data far more symmetric with a much more manageable range. So we're able to actually say something a bit more useful here. Note the change in the skewness from the raw data on the previous slide to the transformation that we have here. Again, we've made the data stay unimodal, but now it's far more symmetric. And then we've also decreased the amount of outliers, and we're actually even able to see that we may have had a few outliers on the small end as well. So many things can go wrong when you're comparing data. So the first thing you want to do is to avoid inconsistent scales, either within the display or when comparing two displays. Now, if you just have the one display, the inconsistency in scale is just that your increments are not staying the same. So you have to make sure you keep your increments of scale the same. So if you're counting by twos, you always count by twos. When you're comparing two displays, this often happens with histograms. You want to make sure that the bin width in histograms are the same when you're comparing two different sets of data. It makes it easier to compare actual centers and actual spreads in those situations. The other way is that you want to make sure everything is labeled clearly so that the reader knows what the plot is displaying. So an example of good intentions but a very bad plot was actually shown on the cover of the Ithaca Times when they are showing concern for the rise in college tuition. So they're actually using Cornell University in this situation. And this is actually an example of a time plot. So in the blue line, we're starting at 1965 and moving all the way up to 1999. But in the orange graph, we start at 1989 and end at 1999. So we're not even starting at the same year, so we can't go and look and say, oh, right here and here match, because that's not the case. The top line is over 30 years, whereas the bottom line is only a matter of 10 years. The other issue is the fact that they're showing in this graph that tuition prices are increasing, and then this orange graph would lead you to believe that their ranking is decreasing. However, if you're plotting these two lines on the same graph, as they are suggesting here, then the values, according to this one, would be increasing. So higher numbers would be up here, which would indicate that in 1999, Cornell University's ranking is like number 1. So again, having things properly labeled is important so readers do not get confused or are not misled. So other things that can go wrong are with outliers and when you're comparing groups with different spreads. So for example, we have these 3 box and whisker plots. Now, the first thing I notice is that they all appear to have outliers, but we're not really sure if these are actually outliers here because we can't see the actual box of those graphs. And the reason is because of the scale. So the scale works for the last box and whisker plot, but it doesn't seem to work for the first 2. So one way to fix this would possibly be to re-express the data, or another way would just be to use a different scale so that you can see what's happening down here. Because as of now, this comparison is useless because we have no idea what's actually happening between these 2 box plots. Other than that, that is it for Chapter 5. So I will see you guys in class tomorrow. Have a great night.